actually, given the mass and radius, you can actually tell what the brightness is. You can actually make a prediction for the brightness. Let me just come to this. So the mechanism that I talked about of dark matter just falling in, that I call kinetic heating because it's the kinetic energy that's heating the neutron star. But then there might be some models of dark matter where a few other things have to happen inside the neutron star, and there's some efficient annihilation going on inside, and that could raise the brightness of the star some more and get you a temperature of 2500 Kelvin. The advantage of that is that at the James Webb, for instance, the observation time required for a 2 sigma sensitivity, 2 SNR, goes down by a factor of 10. If you have that extra luminosity. But that is not, I mean, for that, nature has to have a few more conspiracies going on. For this, I just need to turn on a nucleon dark matter cross-section. Okay? But if nature is kind, you can save a lot of tax dollars and save a lot of money. Right, so again, the point here is you only need 10 power 5 seconds, and 10 power 5 seconds is what? It's the order of hours, right? You only need that to get 2 sigma sensitivity to do some exclusion here. Okay, so this was borne out in a recent numerical computation by these folks, a lot of them from IISc, where they get you sensitivities at JWST with state-of-the-art filter properties of JWST. In particular, they found that the optimal filter to do this would be F150W2, and they show you that if you can get a handle on the mass of the neutron star as a function of the mass of the neutron star, the effective temperature that you can set a constraint on goes like this. These curved jagged lines are basically the SNR. So this is 2 SNR, 5 SNR, 10 SNR. For a neutron star at 10 parsecs. So that's the constraint that you can set, given. Yeah. Yeah, of course.
You said the mass of the neutron star kind of starts from 0.6, so you are also looking into some sort of strange stars and other things?
So this is not me. Yes, but then I would not, I mean, for some equations of state,
you can pull it down.
You can pull it down to 0.6.
Oh, yes. I was not aware of that.
These are extreme, but neutron stars, not strange stars.
Okay.
Yes.
Thank you. I was not aware of that. Thanks.
Okay. So before I get ahead of myself, let me pause and go over the difficulties of this program again. All right. So. First of all, these old cold neutron stars must turn up in radio telescopes or infrared surveys, and lots of astronomers tell me by making back-of-the-envelope estimates that it is possible, but then they still have to turn up in nature, right? So that's there. And then there's the fact that every day we learn something new about neutron stars. We don't know really what's going on inside there. There are some kooky magnetic fields and rotochemical heating and things like that. So something else might be heating up the neutron star from the inside, especially at low temperatures where we haven't seen neutron stars. In other words, as a particle physicist, I would say the internal backgrounds are not entirely understood. You also really need to know what the age of the neutron star that you're looking at is, right? Because maybe you see a 3000 Kelvin neutron star, but maybe it's not so old. We do have good handles on what the age should be using spin down, but that gives you an order of magnitude, but it's not entirely reliable. You need more handles to pinpoint the age. So given all this, I would myself admit that if we see a neutron star burning at 1750 Kelvin, say, then a claim of a discovery would definitely be premature or exaggerated. However, what cannot be argued with is, sadly, that if you wanted to see a 1750 Kelvin neutron star, stared at it for whatever number of hours, and you didn't see anything, you didn't see photons coming out of it, then you can be sure that you have excluded the parameter space. In experiments, exclusion is always cleaner than discovery, right? So given these challenges, what really do you buy? Do you really need to pump in money and effort into this? In other words, does this mechanism of dark kinetic heating of neutron stars really expand our search frontiers for dark matter? So that's what my next few slides is going to be on. For comparison, here is an eagle's eye view of all the constraints of dark matter searches looking for dark matter nucleon scattering on Earth so far. Okay? Notice that the x-axis now spans 20 orders of magnitude in mass in a range where we think dark matter should be a particle. The y-axis of cross-sections scans around 40 orders of magnitude. And there's so many combinations of experiments that constrain dark matter cross-sections here. If we find a neutron star not glowing at the correct temperature, then here's the parameter space that you would rule out, all the green stuff. Okay? And of course, if you want to set stronger limits than this, then you look for colder and colder neutron stars, and that would take you farther and farther down. So let's go over this a little bit. Why does the neutron star detector do so many orders of magnitude better than dark matter detectors? Let's begin with a basic comparison. Let me zoom in again so that the y-axis now spans 3 orders of magnitude. Here are some terrestrial constraints. Well, this is not the most latest. This is not the latest. This is Panda X, but then Xenon 110 goes 2 orders of magnitude lower than this. Nevertheless, the point here is that here's a basic comparison where if I have a 1750 Kelvin neutron star detector, all the cross sections above the red line can be ruled out. Okay? The reason it's flat is that the rate at which kinetic energy is being dumped into the neutron star by dark matter to the first order does not depend on the mass of the dark matter. Because the fewer particles, I mean, if you have more number of particles falling in, it means that the number density is high. It means that the mass of dark matter is small, and that compensates. The mass and the number flux compensate for each other. And this cross section in particular is the threshold cross section, or to be even more precise, the geometric cross section of dark matter falling into a neutron star. In other words, this is the minimum cross section I need to ensure that as the dark matter transits the star, there is at least one hit in the star. Okay, and that one hit will ensure that the dark matter gets captured in the star and transfers the kinetic energy. And of course, if I'm looking for a colder star, 1000 Kelvin, I can go down by 2 orders of magnitude and so on. So already on this plot, I can complement dark matter direct detection experiments because of this feature. Now, if I were to go to low mass, the low mass frontier is it's something that experimentalists are looking for, sub-GeV dark matter. In the low mass frontier, dark matter experiments, terrestrial experiments couldn't really, they don't really have great sensitivity because dark matter is so light that it doesn't really produce recoils in nuclear targets, especially when the dark matter is lighter than the nuclear target. Whereas in neutron stars, you don't really have that restriction. What you do have instead is polyblocking, because remember the neutron stars are Fermi degenerate objects. So the neutrons are in a Fermi sea, and so there's only a fraction of neutrons that you would excite with dark matter hitting it. So accounting for that fraction, you lose sensitivity as you go below masses below a GeV. Okay. And then I'm zooming out now. So now notice that the y-axis goes all the way to 10 power 11 GeV. At high masses, especially about 10 power 6 GeV, neutron stars still do better than direct detection experiments, but then you start losing sensitivity now because the one recoil is not enough to capture in the star. One recoil is not going to dump in enough energy to be below the kinetic energy of the dark matter far away from the star. Okay, which is the condition for gravitational capture. So I need to increase my cross section to ensure that there are multiple scatters so that I dump all the kinetic energy that I started out with and get captured in the star. And then here's a fun thing. What if the dark matter nucleon cross sections are really high, like stronger than strong cross sections. There are some crazy models that can give you this. So in that case, I'm not showing this in this plot, but these terrestrial experiments actually lose sensitivity if the cross section is too high. And that's because dark matter would get slowed down or even trapped in the overburden, which is the Earth's crust or even the shielding of the detector. And so it would never reach the actual fiducial volume of the detector. Neutron stars, to a first estimate, don't have this problem. You can scatter in the crust, or there's really nothing getting trapped in the outer shell or anything like that. Okay, now the theory of dark matter could be such that interactions can only happen via a spin-dependent term. In that case, direct detection underground experiments lose sensitivity because they don't enjoy the coherence of dark matter scattering across the entire nucleus, which gives them an enhancement in the cross section. And that's why you'll always see that spin-dependent limits are always pretty weak. Whereas, maybe I'm not showing the spin-dependent cross-section here. Sorry, the spin-dependent cross-section is actually weaker than what I'm showing here. But for neutron stars, you don't really care because you are scattering directly on nucleons, not on nuclei. So what you see is what you get, and that's why you're able to, you can always do better than spin-dependent direct detection exclusions. Well, here's a paper we recently wrote at Triumph, exploring a specific model for this with dark matter mediated by a pseudoscalar. I'm sorry about that. So the point here is that you could have a mediator or an operator such that the scattering between dark matter and nucleons is suppressed by the dark matter velocity. Okay, the operator structure gives you velocities in the non-relativistic limit. And in direct detection experiments, you almost cannot see this because the dark matter is flying in very slow here, only 1,000th the speed of light. And if the cross section goes as 4 powers of the velocity, for instance, you really don't see this at all in the terrestrial detectors. But in neutron stars, the dark matter is flying in at semi-relativistic speeds, almost the speed of light, and so this plot still remains. Okay, so you can still see it here, and that's what we had explored with an explicit model. So let me wrap this up quickly, this part. So maybe the theory of dark matter is such that there is an approximate symmetry in nature, so that dark matter can only scatter inelastically by transitioning to some excited state, not dark matter to dark matter, but to some other excited state. In that case, what you're really limited by is what is the mass difference between that excited state and the ground state of dark matter. Okay. In direct detection experiments, you cannot really probe above mass splittings of 100 keV. Again, that's because dark matter is flying in only at 1,000th the speed of light, and that's all the recoil energy that you can actually tolerate. Whereas in neutron stars, again, the dark matter is flying in at relativistic speeds, and so you can actually go to mass splittings of up to a GeV, which is 4 orders of magnitude larger than direct detection experiments. Okay, and lots of nice papers have been written about this with explicit models and operators. Finally, there is an impending irreducible background coming up for dark matter experiments, underground experiments, known as the neutrino flow, where these neutrinos are sourced by the sun, by cosmic ray collisions with the atmosphere, and so on. Here I've drawn the xenon neutrino flow in dotted curves. And as you can see, so this is an irreducible background. So when they hit this, they cannot move any further. But for neutron star detectors, you don't have this constraint. There's no neutrinos falling in to heat up the star. And as you can see, for spin-dependent scattering, we actually start below the neutrino flow. Okay, so you could say that neutron stars terrifically complement dark matter experiments. Okay, so that's the basic idea. There are some important variations on a theme. Maybe I won't go into it in too much detail. For example, it's important to know whether dark matter thermalizes within the neutron star, because only if it refrigerates well enough does it collect in a small ball in the center of the star. Only then can you ensure the efficient annihilation of the star and increase the temperature and maybe help the telescopes. Whether this happens or not is a model-dependent question. So that's what we worked out. You can also ask, what if dark matter doesn't like neutrons? What if dark matter only scatters with electrons, or maybe just muons? Because we really don't know what its microscopic identity is. Thankfully, neutron stars have huge populations of protons, electrons, and muons. Because of beta equilibrium, the kinematics is now a little bit non-trivial because electrons are relativistic in the star. Nevertheless, we did it, and we have some nice results on that. Maybe, okay, this also let me go through very quickly. So you can ask, what if dark matter doesn't scatter in the core of the neutron star at all? Because we really don't know, we really don't know what the core is made of. High density QCD does not give an answer to that. Maybe there's some phase transition going on, and then you have quark matter and meson condensates dominating the core of the star, in which case dark matter scattering dynamics is not very clear. So somebody could be really skeptical and say maybe dark matter doesn't scatter at all in the core. Maybe it's super suppressed. What happens then? Doesn't matter. We still have the crust. And the crust is sort of the second densest object in the world. And we understand the crust really well. The only thing is, as we go deeper into the crust, the knowledge of the structure of the crust becomes more uncertain. Nevertheless, we have a pretty good physics handle on what the crust has. My favorite is the bottom layer of the inner crust, containing all these weird nuclear shapes, gnocchi, spaghetti, lasagna, bucatini, Swiss cheese. So it's literally called the pasta face. These are reshaped nuclei due to competition between Coulomb forces and nuclear forces. But there is a way to calculate dark matter scattering on each of these sublayers. So we did that. And here is the sensitivity of the pasta face, which actually sets the main sensitivity of the crust, compared with dark matter experiments. I'm showing spin-dependent scattering here to be optimistic. And you can see that even using just the crust of the neutron star, you can do better than dark matter experiments for many scenarios, especially at low mass, right? Okay. So Susmita touched on this briefly. Dark matter need not be a smoothly distributed floor in the galaxy. Maybe it lumps. This could happen in a lot of non-standard cosmological models in the early universe. People study this a lot. So maybe dark matter is in the form of some substructure, subhalos, and so on. That's what this picture shows. This is the dark matter halo, and these are dominated by subhalos. In that case, maybe the Earth is between two subhalos right now, and the 40 years of looking for dark matter is futile because there's really no dark matter passing through the Earth. So what do? Well, neutron stars to the rescue. These subhalos could be encountering neutron stars over cosmological time scales, and every time an encounter happens, you could heat up the star, and maybe you could look at so if you do a survey of nearby neutron stars, maybe you can always find a fraction of the neutron stars at a high enough temperature that's within your telescope sensitivity. So that's what we calculated in this paper, and we showed that there are vast regions of parameter space in subhalo radii versus subhalo masses, where you could use the dark energy survey and Rubin or LSST to look for a requisite number of neutron stars burning at a requisite temperature. Okay, so there's a lot more going on in this plot, but then for lack of time, I'm just going to skip it and go straight to. So I have 15 minutes left, right? How much? Oh, I have half an hour left. Okay. Then sorry. Then let me actually talk about this plot a little bit more. So one neat thing here is that using this, if dark matter is lumping up into these subhalos, we found that you already have a constraint on this sort of lumping from the coldest neutron star observed, and that happens to be in this slice, the orange slice. And for this to really happen, you need the lump not to get disrupted when it's passing through the neutron star. In other words, you need some self-interactions among the dark matter particles for the lump to stay intact. Nevertheless, it could be done, and you have Bondi accretion of dark matter into the neutron stars that heats up the star to above 40,000 Kelvin, and that already sets a constraint. The other thing I want to point out here is that the region of parameter space that you could constrain, if you look at the the x-axis, these are pretty light subhalos as far as subhalos go. So these subhalos are 10 to the minus 12 and below solar masses in mass. These are basically small asteroids, small asteroid masses and so on. That's interesting because almost nothing else can probe the parameter space at these small masses. Okay, there's a lot of limitations coming from, for example, gravitational microlensing surveys that look for these subhalos. And looking for excessive gamma rays and so on, which I have not put on this plot. So really there's a very challenging region down here that can be probed by this sort of thing, neutron stars heating up. Right. Okay, so then let me switch gears a little bit and talk about the other mechanism that gives us orders of magnitude improvement in dark matter searches using neutron stars, that which I call an internal fire. So now this has more knobs on it. So in the previous mechanism, I just had to turn on a dark matter nucleon cross-section like the underground experiments have been doing for 40 years. This works out only in a few specific models. So let me take some time to introduce this model. It's not a particularly baroque model, trust me. It's not hard to follow. So in this model, you hypothesize a new particle, let's call it chi, and characterize it thus. It's charge neutral under all fundamental forces of the Shannon model. Let's give it a spin half, make it a fermion, and the special thing here is I'm going to give it a baryon number 1, okay, and we'll see why. Okay, so if I characterize a particle just this way, the disgruntled ghost of James Chadwick is going to come up and say what I described is just a neutron, right? So what are you talking about? Of course, depending on the flavor structure, this could also be a lambda baryon or sigma baryon or delta baryon and so on. And James Chadwick wouldn't be wrong. What I described is a neutron, but this is an exotic neutron. That which, I mean, I call it a dark neutron, some people call it hidden neutron, sometimes it's called mirror neutron and so on. The difference between this new neutron and the old neutron we know and love is that whereas the standard neutron, we really know what its mass is up to 4 decimal places. We don't really know the mass of the dark neutron. But because they have the same quantum numbers, I can set up a two-state Hamiltonian that looks like this with the bare masses in the diagonal terms. And because in quantum field theory, if something is not forbidden, it is compulsory, I have to write down an off-diagonal term as well that leads to quantum mixing between the neutron and the dark neutron. Okay, quantum mixing is not really new. We all know this. We've seen many examples in nature. Famously, the photon mixes with the rho meson, so sometimes we are seeing literally with the rho meson. At high energies, close to electroweak energies, the photon mixes with the Z boson, which is what helped us discover the Z boson in the first place. And there's a lot of buzz these days about neutrinos, neutrino flavors mix among each other. And lead to spectacular phenomena like neutrino oscillations, which is what helped us know that neutrinos have mass, right? So when you have mixing, you have a lot of interesting consequences, and consequences for neutrons are, for example, neutron oscillations, which can be depicted with a figure like this, where Oh, I had a cricket figure, but I think I changed to baseball in the last minute. So you have a pitcher on this side throwing a neutron at a wall, and there's a batter on the other side waiting for it. The wall could detect the neutron as a dark neutron in its interaction eigenstate state and let it through, and the batter on the other side could again see it as a neutron. So you can have neutrons shining through a wall sort of experiments. And we explored that in some detail. Then another interesting thing you could have is neutrons, although they are charge 0, electric charge 0, they do interact with light through magnetic dipole moment. That is how you can actually trap neutrons or control neutrons with magnetic fields. So here's a vertex for that. Just imagine this is also a blue circle for neutrons. That if this had been blue, then that would have been an actual neutron magnetic dipole moment. But because you have mixing with the dark neutron, I can replace one of them with a dark neutron. So I have instead a transition dipole moment, which is this vertex, through which I can have neutrons decaying to dark neutrons, emitting a photon, or vice versa, dark neutrons decaying to neutrons and so on. Okay, yes, please. Oh, 6 minutes. Okay. Sure. Okay, so what am I solving here? Why do you need to contemplate dark neutrons? Well, the dark neutrons could actually very well be the dark matter of the universe. There are some cosmological arguments for this that we had worked out, which I'm not going to talk about here. But you could very well have these dark neutrons living longer than the age of the universe, for them to constitute the dark matter of the universe. They could have been in chemical equilibrium with baryons in the early universe, so they make up, they have comparable densities with baryons. So that's one pretty important reason. There are other reasons too, but because this is a dark matter talk, I'm just going to stick with that. Now, what do neutron stars have to do with all this? Okay. Neutron stars, again, to introduce them in a different way, we know that they contain 10 power 57 neutrons and a 10% population of protons, electrons, and muons due to beta equilibrium. But the other picture of neutron stars that we have is that in energy space, the nucleons fill up a Fermi sea of all these energy levels, like any closed quantum system. And the Fermi energy of this Fermi sea is typically around 100 MeV, right? So the idea here is to use all the energy stored in this Fermi sea as a battery to heat up the neutron star, okay? And let's see how that can happen. That can happen if you have dark neutrons in nature. That's because neutrons could, if kinematically allowed, and in neutron stars they're pretty kinematically allowed because of self-energies and so on, neutrons could decay to dark neutrons, and depending on the exact model, dark neutrons plus something else in the final state. Or neutrons could find other neutrons or protons, the other constituents of neutron stars, and in that collision process, one of the neutrons could transform to a dark neutron. Through any of these mechanisms, you lose a neutron from the Fermi sea. Okay, so you create a hole in the neutron Fermi sea. And nature abhors holes, as we know. So when you create a hole, all the other energy levels above are going to fall down to fill up the hole very quickly. And in physical space, you have an actual, you create an actual hole. The surrounding neutrons are going to rush in to fill up that hole. That's going to lead to a frenzy of electromagnetic and kinetic energy being dumped into the material of the star. This is not a new effect as such. We have seen this in semiconductors, and the semiconductor people call it the Auger effect of electrons in semiconductors. It's used to treat cancer and so on. But I realized that this exactly applies to neutron stars as well if you have dark neutrons. So I call it the nucleon Auger effect. It's a heating mechanism that, as far as I can tell, nobody had written down before. The cool thing is, because you have so many 10 power 57 neutrons and protons, this is happening all over the neutron star, and that gives you an explosive liberation of energy inside the neutron star. Okay? And that means the coldest neutron star that we've observed, the 42,000 Kelvin neutron star, could now be used as a suitable lab to set constraints on this kind of dark matter, dark neutron dark matter. And in particular, the age of this star becomes relevant. It's 300 million years old. It's relevant because the time scale of this process, of these processes, the collisions and the decays and so on, I want the time scale to be longer than the age of the star. That's because if this happens too fast, then this process has ended, and when I'm looking at the neutron star now, nothing is going on. So I need the heating to be happening now. So I want the time scale to be longer than this. So I want the luminosity to be higher than this, and the time scale to be longer than this. So that gives you constraints from two different ends. And of course, the research I had done on looking for neutron stars in the first method, the external fire, that also becomes relevant, because in the future, you can always use James Webb and other telescopes to look for 2000 Kelvin neutron stars, and that should obviously give you much stronger constraints than looking at a 40,000 Kelvin neutron star, right? So you could use these as future labs as well. Now here's a little bit more detail on how I do the calculation. To set constraints, I demand that the heating rate, the internal heating rate, is smaller than the cooling rate, which again model as a black body, like everyone does. The heating rate is given by an integration over the volume of the star times the number density at a given radius, the neutron number density, times the rate at which energy is released due to this hole formation in the Fermi sea. So the one non-trivial, I don't have a slide, sorry. The one non-trivial thing here is to calculate this rate. I have a backup slide for that, I can talk about it later. So that has to be done a bit carefully using state-of-the-art nucleon potentials and so on, but it can be done, and that's what I did. And I can see Gopu taking the mic out, so let me just finish. So here are some constraints on this mechanism. On the x-axis is the temperature of neutron stars that have been observed. Y-axis is a proxy for the mixing angle between neutron stars and neutrons and dark neutrons. Okay, this is off-diagonal element basically. So the blue line up here was the constraint, the strongest constraint before I got into this. That comes from looking at binary pulsars. But as you can see, you can go down orders of magnitude using neutron stars. These are the ranges that can be constrained. So let me just compare it with searches for these kinds of transitions at terrestrial facilities called ultra cold neutron facilities. These are basically bottles in which you put neutrons, and the neutrons are going around very slowly. Okay, and you look for neutron disappearance from these bottles. So from that, a lot of fine experimentalists have set impressive constraints. So don't mind the x-axis. The important thing is the constraints are at the level that seem to be comparable to the level at which I'm setting bounds. Right, my bounds are all in the red shaded region, whereas their constraints seem to be at the same in the same ballpark. But the thing is, their constraints are only valid for dark neutron masses that are apart by just 10 power minus 18 MeV, because their sensitivity goes down very quickly if that splitting is larger than the Zeeman splitting from the Earth's magnetic field. Okay, that's how the Hamiltonian goes for them. Whereas for me, my constraints hold for mass splittings up to 10 MeV. So that's what, 19 orders of magnitude. So we can actually do better than terrestrial experiments by in 19 orders of magnitude of parameter space and rule this out. So I'm summarizing all this again with the plot with the slide I showed in the beginning. So we have two different mechanisms now. All these amazing telescopes would become super relevant to directly probe fundamental physics and where we can learn something really deep and interesting about nature. And my hope is that in the near future, maybe dark matter would remain dark and ubiquitous and plentiful. Hopefully, it will no longer be mysterious and we can move on to do something else. So thanks a lot. I'm happy to take more questions.
Thank you for a very wonderful talk, and very complicated things kind of told to us in a very kind of pictorial manner. Very nice. Thank you. Questions from younger colleagues? Yes, Jacopa.
Hi. So I had a question in the first part, that is the external fire.
Yes.
So I'm just wondering, how does the sensitivity curve which you showed change if I use, say, a steeper equation of state or a softer equation of state? Is it dependent on the equation of state drastically or something? Like even in the passive structures, if I change the equation of state, the structure would change, right? I mean,
Right.
So
Let me answer saying it doesn't depend on it dramatically. It depends on it somewhat. It depends on it within an order of magnitude. The equation of state ultimately tells me what the mass and radius is. That changes the threshold cross section. It also ultimately tells me the radial profile of the neutrons and protons sitting inside the star. So that gives me, a radial profile of the Fermi densities, for the Fermi momenta as well. So all these effects kind of, they don't all work in the same direction. One compensates for the other and so on, and you end up within the same order of magnitude, all the sensitivities. And having said that, let me just flash this plot again. This I didn't make, these authors made. The curves that you see here are actually, I think I should use the word averaged here, averaged over very many equations of state before they give you this. I don't know if it's average or integrated or whatever. Yeah.
okay. Yeah, thank you.
Questions from?
Unfortunately, we got disconnected over Zoom.
Okay. Okay, that's fine. It happens. Okay, so then can we ask questions from the YouTube lecture then?
Yeah.
If you have no further questions from here. Oh yeah, please.
So you have already told maybe, so how the dark neutron are arising actually?
Good. So, yeah, I thought I wouldn't have time for that, so I think I skipped those slides. In a model perspective, right?
Yes.
You're asking how would a dark neutron come? Oh, I don't have a slide. Okay. So, the dark neutron could either be an elementary particle.
So that's why you're saying when it is decays into dark matter or what?
Yeah, but then it doesn't have to be elementary.
Okay.
It could be a composite particle
Okay.
coming from some sort of hidden QCD.
Okay.
And what people usually do is they assume there's a mirror sector for the standard model, and so there's mirror QCD and mirror composites, and so you get a dark neutron from that. But it doesn't have to be. It could just be an elementary particle. You can write down a Lagrangian at the hadron level, and then you can UV complete it with a dye quark, for example.
Okay.
And the dye quark is safe from bounds and so on, and that could do it.
Okay, so when you are telling it is dark neutron, so already neutron has interacted with the dark matter or what? Or it is completely different thing?
No, it's a completely different thing, completely exotic object.
Okay, so then what is its distribution within the neutron stars?
So good. So in the neutron star, if these processes happen fast enough, faster than the age of the star, then maybe the neutron stars that we are looking at right now are admixtures of the dark baryons, the dark neutrons and the neutrons.
Yeah.
But if they are pretty slow, maybe they're just now these transitions are happening. In that case, they are still mostly neutron stars.
Okay.
Some of them are still.
So how to differentiate? I mean, observational or
Right.
what?
So if it is happening, if this is happening on a time scale longer than the age of the star, then you get a lot of constraints, and maybe you will see this in the future. Maybe it's just happening such that the temperature is only about 2000 Kelvin, and maybe you will see this in the future. But if it's already happened, one way to see this is it will modify the equation of state of matter inside the neutron star.
Okay. Yeah.
Because it will soften there's no self-repulsion here.
So
In a minimal
also-
model, there's no self-repulsion, and
Okay.
it softens the equation of state, so you get
Then
modifications. to
it
matter.
should have effect on the macroscopical properties of the neutron star.
Yes, exactly.
And
It
how
will
that, if you say? Yeah, sure.
Maybe this can be.
Yeah.
Sure.
So, no, it's
No,
amazing. Please continue. There are other questions. No. Okay. Anyone else? I have a bunch of. Oh, you have a question. Go ahead.
Actually, maybe. So what he was asking, so is there anything more we know about this dark neutron? Say, is there elementary magnetic moment different, then it can give rise to a different magnetic field of neutron star?
Okay. So that depends entirely on the model of this dark neutron. People who strongly believe that the dark neutron has to come from mirror sectors also put in these mirror photons, and they do create mirror magnetic fields on Earth. So for example, this plot that I showed, the y-axis is, the x-axis is this hypothetical mirror magnetic field for these searches. But it depends on your degree of belief. For me, I only want to turn on the most minimal thing to see this. But yes, it's an interesting idea. You can probably have huge mirror magnetic fields in the neutron star.
If there is a more fraction of dark neutron.
Exactly.
Yeah.
Although I want to say, let me just finish this. So although I want to say, my understanding is in standard neutron stars, the magnetic field is inherited from the progenitor, right? And then it becomes stronger. So maybe you need to start with some mirror star, and then it collapses to some mirror neutron star, and then that's how you get the magnetic. I don't see a way in which you can get a magnetic field through this mechanism, where the neutrons go to dark neutrons.
I have a bunch of questions. We
Yes.
can discuss this offline too. So this is about. So there are. I remember a paper by Thibault and his collaborators talking about a WIM particle can get actually trapped in the solar system, and so blah blah blah.
Yeah.
So that way, if you're looking for, since many of the neutron stars in binaries, I don't know about that specific cold one, may not be. So this is an added attraction. You can just look at the paper by Thibault and see whether that can be adapted to argue that millisecond pulsar, so binary, can be more susceptible to dark matter kind of particles because they get because of their non-Newtonian kind of in the solar system there are perturbation from other planets and other things. So
right.
That's a possibility you may.
Right. So I've seen an argument due to Annika Peter that the capture in just the solar system, not on the Earth, not in the Sun, capture in just the solar system eventually doesn't work, because whatever leads to gravitational capture, there will be something else that kicks it out. Over long terms.
If I remember, this was I was a grad student in those days. So this was it's not just he argued that it should hang around till 10⁻⁹ years or something. This is a special class of beams. I don't remember all that. I was kind of. And just a follow up on this, there are this. I'm not sure. It's called. Magnificent Seven or Seven Sisters or something. So they are the nearby neutron stars.
Yeah.
They are actually an optical observation, right? If I'm not mistaken, I forgot.
X-ray.
X-ray observation. Yeah. Yes. So are they? Followed it up with kind of electromagnetic, kind of optical observation to see some constraints.
Right. So we looked into this a little bit for this paper. Because this is a paper in which so in the mechanism up till this point, you can only heat it up to 2000 Kelvin. So if the Magnificent 7 is getting heated up by this mechanism from smooth dark matter, you're not going to see it. It's going to be buried under all the X-ray luminosity.
Sure.
But in this mechanism, where the dark matter is not smooth, it's lumped, the lumps can temporarily heat the neutron stars to 10⁶ Kelvin and so on. And 10⁶ Kelvin comes into the X-ray range. So we got excited about that. We looked into it a little bit, and we found that with the current sensitivity, so this was the Magnificent Seven was discovered with Rosette, I think, Rosette satellite.
Yeah, that's
With
right.
Rosette, they couldn't really do it. Maybe the future Rosetta or something maybe could do it. We haven't
It's
studied.
already,
Oh, it's already there. Okay, okay.
So,
That's my ignorance.
no.
So yeah, maybe. We just didn't know how to really estimate it because it was too hard an astronomical calculation for
So
us.
in that case, you don't need to even look for pulsars as such.
Yes.
Because there are these LMXBs,
Yeah.
low mass X-ray binaries, and they actually have these nuclear detonations.
Okay.
And so it's actually spreads like, you can actually do this in the next nearest neighborhood kind of a statistical random walk. That's how the explosion kind of proceeds. But then you may want to wait because these things go down fairly rapidly in a month's time and see whether there are this additional signature what you are looking for. And I think the current telescopes may be good enough for those purposes.
Okay.
So
I
when
would love to discuss.
when you come over to TIFR, go and talk to Sudeep
Yes,
Bhattacharya,
okay.
who's kind of works quite a lot on these things.
Okay,
So it'll be
okay.
amazing.
Absolutely,
Okay,
absolutely,
Great.
yeah.
Thank you
Thanks
very
for
much for all the wonderful questions too. So this session gets over now. We have half an hour. We'll be delayed by, let's get together. What time we should come back? It's it's already 11:50. So we have, okay. Okay, sure. So we have now only a discussion. That's what where is my program? I think we have a discussion for 1 hour. We can cut it down to maybe some, a bit less. Okay. Thank you.
Hello, hello, mic check. Hello, hello, hello. Hello, mic check 1 2 3. Hello. Hello, hello, mic check. Hello, hello. 1 2 3. Hello, hello. Hello, hello, mic check. Hello, hello, hello. Mic check 1 2 3. Hello, hello. Hello, hello, mic check. Hello, hello, mic check 1 2 3. Hello, hello. Hello, hello, mic check. Hello, hello, hello. Hello. பாட்டு பாடுறேன்.
Hit a wall. Right now, I need a miracle. Hurry up now, I need a miracle. Stranded, reaching out. I call your name, but you're not around. I say your name, but you're not around. I need ya, I need ya, I need you right now. Yeah, I need you right now. So don't let me down. I think I'm losing my mind now. It's in my head, darling. I hope that you'll be here when I need you the most. So don't let me down. 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 Running out of time. I really thought you were on my side, but now there's nobody by my side. I need you right now. Yeah, I need you right now. So don't let me down. I think I'm losing my mind now. It's in my head, darling. I hope that you'll be here when I need you the most. So don't let me down. Don't let me down. Don't let me down.
sympathy, I hope you can show me. If you wanna go, then I'll be so lonely. If you're leaving, baby, let me down slowly. This night is cold in the kingdom. I can feel you fade away. From the kitchen to the bathroom sinking. Your steps keep me awake. Don't cut me down, throw me out, leave me here to waste. I once was a man with dignity and grace. Now I'm slipping through the cracks of your cold embrace. So please, please, could you find a way to let me down slowly? A little sympathy, I hope you can show me. If you wanna go, then I'll be so lonely. If you're leaving, baby, let me down slowly. Let me down, down, let me down, down, let me down, let me down, down, let me down, down, let me down. If you wanna go, then I'll be so lonely. If you're leaving, baby, let me down slowly. Cold skin, drag my feet on the tile as I'm walking down the corridor. And I know we haven't talked in a while, so I'm looking for an open door. Don't cut me down, throw me out, leave me in a waste. I once was a man with dignity and grace. Now I'm slipping through the cracks of your cold embrace. So please, please, could you find a way to let me down slowly? A little sympathy, I hope you can show me. If you wanna go, then I'll be so lonely. If you're leaving, baby, let me down slowly. Let me down, down, let me down, down, let me down, let me down, down, let me down, down, let me down. If you wanna go, then I'll be so lonely. If you're leaving, baby, let me down slowly. And I can't stop myself from falling down. 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 Could you find a way to let me down slowly? A little sympathy, I hope you can show me. If you wanna go, then I'll be so lonely. If you're leaving, baby, let me down slowly. Let me down, down, let me down, down, let me down, let me down, down, let me down, down, let me down. If you wanna go, then I'll be so lonely. If you're leaving, baby, let me down slowly. If you wanna go, then I'll be so lonely. If you're leaving, baby, let me down slowly.
ਅੱਲਾ ਦੀ ਕਸਮ ਤੂੰ ਮੈਨੂੰ ਇੰਨਾ ਪਿਆਰਾ ਹੋ ਗਿਆ ਹੁਣ ਤੇਰੇ ਬਿਨ ਨਾਮੁਮਕਿਨ ਕਰਨਾ ਗੁਜ਼ਾਰਾ ਹੋ ਗਿਆ ਅੱਲਾ ਦੀ ਕਸਮ ਤੂੰ ਮੈਨੂੰ ਇੰਨਾ ਪਿਆਰਾ ਹੋ ਗਿਆ ਤੇਰਾ ਲੜਨਾ पर हो गया सड़िया नहीं मरिया नहीं दुपट्टा तेरा जीनू छो गया तू चुम्मिया सी जो परिंदा कदे हो मैं सुनिया पर हो गया तेरी चांदर भी जन्नत है तेरी कमीज जन्नत है हो जन्नत है तेरा हंसना तेरी हर चीज जन्नत है हो जन्नत है तेरा हंसना तेरी हर चीज जन्नत है
Hello, hello, check. Hello. Hello, hello, check. Hello, 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 check, check, check. Hello.
Hello, hello. Mic check. Hello. Hello, 1, 2, 3. Hello.